but it's not necessary you need to do that. Now it's to Ellie.
Hi, I'm Ellie. So, there are just a couple things I want to highlight on. I think Rachel and Keisha have covered it pretty well, but can we just take a moment and consider what the purpose of university is and what the purpose of this course is, right? So, I mean, I think we can all agree that it's to prepare ourselves for the future, right? To learn things, to improve on ourselves, and basically to be able and be in a position to go out into the world and do noble things for the good of all, or whatever you'd like. So, considering the general goals of that, of the university, of coming to class, do you understand the purpose of homeworks? Because I think that a lot of times we get caught up in the idea of what is my grade going to be, right? Rather than the actual purpose of it, which is to practice working on something, to learn how to approach problems, and ultimately to have new skills at the end of this. And if you're just looking up things on the internet without bothering to understand them, then you are not only, as Rachel and Keisha have mentioned, inflicting some degree upon your peers and on your TAs, you are harming yourself because you are depriving yourself of an opportunity to improve. So, one quick note about use of the internet. I mean, it's great, right? We can consider a lot of issues of equality when thinking about the internet, but also think about how if you understand something, you shouldn't really need to be looking at the resource that you're using to understand it. So if you want to use the internet, that's great. But if you are concerned about avoiding plagiarism, a really good rule of thumb for that is if you're using the internet to understand something, then when you go to write something down about it, stop looking at the source. So that's just sort of a note of practicality for that. Yeah.
Okay, and we're just going to say one more thing, just maybe to clarify, because I'm sure some of you guys come to office hours like every single week, spend your lives there, and now you're like hearing this announcement, and you guys are like, oh my God, these guys are nuts. So backstory, all of us, this is our second semester TAing this course, and we're going to tell you what happened our first semester. So our first semester, we graded the midterm. They didn't have a lot of homeworks in the class, so we had only really seen one assignment from them before we graded the midterm. We graded the midterm, and a lot of it was straight from the internet, which, as you know, you're not allowed to use the internet during the midterm. So we came in, we had a very similar announcement during class, except probably a little bit more intimidating. And we said that they had 72 hours to come forward and admit that they cheated on the midterm. So you think, okay, maybe some of them are going to come forward, maybe some of them are going to risk it. 35 people came forward. Those are the ones that were like felt guilty about it. We had 20 more people on our list. This was in a class much smaller than yours, 130 people in this class, and we had a list basically of 55 people that had used internet resources on the midterm. So we were lenient with those who came forward. They got a maximum of 2 letter grades off their final. That means a maximum grade of C in the class. The ones who didn't are failing the course, and 2 of them are in honor court right now. So I'm sure none of you guys want to risk that. Learn from their past experiences and don't do that so that we don't have to go through that again, because none of us wants to. It was like kind of a terrible experience for everybody involved. You know, administrators get involved, students get involved, parents get involved. Nobody's happy about it. So on that note, enjoy today's lecture.
Any questions about any of this? What you're allowed to do, what you're not, you know, maybe some of you aren't clear about what constitutes cheating or plagiarism or, you know. So, for example, copying an answer from the internet and just changing all the variable names, that's cheating. That's not putting in your own words. That's not understanding what you're writing. And some people, we call them into office hours. We ask them to explain their answer on the homework, and they couldn't explain it. Remember, there's red letters on each assignment and on the website, on the course syllabus. Do not submit answers that you not fully understand. How many of you remember seeing that many times? Good. Many of you have done exactly that. So please stop doing that. These are your peers. These are the TAs. If they want to take you to honor, I can't stop them. You know, I try to be a nice guy, and I try to give people the benefit of the doubt and be lenient. But they can take you to honor, and it's their prerogative. And it's between them and you and honor, and I'm not even involved. And they have taken people to honor before, last semester. And these people are not having a good time. And neither are we. I mean, it's very awkward for us, too, to have conversations like that. Right? Question?
So I know, like, on the homeworks, on the exam, it said, like, try and keep your answers, like, on the shorter side. In the future, can we make our answers maybe a little bit longer to make sure that we, like, fully explain the concept?
Oh, you're free to fully explain it even on the exam. It says, first state the short answer version, just so we all agree on what the crux of the answer is, whether it's diagonalization or dovetailing or pigeonhole principle or some other short phrase. But then you can explain as much as you want. And you can even add extra sheets, to the PDF file, explaining it even more. Now, most of these questions do not require that long of an explanation. And by the way, when you copy from the internet, it's extremely, extremely obvious to us that you did that. Even if you change all the variables and flip a couple of sentences around, it's still 99.99% crystal clear to us that you've done that. We know where all these answers are. We've been teaching it for many years. We know about Chegg. We know about Stack Overflow. And if we Google one of your answers and we see it on the internet, that's clearly where it came from. Remember, Google works both ways. I'm not sure if you're cognizant of that. If you Google something and find it, we Google your answer, we will find that too, even though we probably already know about it. After grading hundreds of assignments for several semesters from these, they know where all the answers are on the internet. And by the way, when you copy from the internet, often you copy wrong things. In fact, it's worse than that. Some people deliberately post on the internet wrong answers on purpose for you to find, so that you're copying them wrong, and that you'll get a lower grade, or you'll be caught cheating, because now there's a very clear fingerprint, because that error is very esoteric. And they deliberately put it there like a landmine for you to step on. How many realize that? We mentioned that before. So it gets very Machiavellian. Some of you are working at odds with others, so people do that. So going to the internet is not safe harbor to learn this stuff, and to, you can use it judiciously, you can use it in a good way, but when you copy off each other, when you copy off the internet, it's extremely, extremely easy to detect that. It's not even fuzzy, for the TAs, or for me for that matter. So it just creates a lot of awkwardness, and we really rather not have these kind of conversations. Multiple people have failed the course because of the last semester. I hope that's not going to repeat here. Especially if you needed to graduate, that means you won't graduate. Or if it gets to honor, you may be expelled. And they can take you to honor. It's not even up to me. Honor system, honor code works here. It's by students, for students, run by students, and professors hardly get involved with it unless they call in as a witness or something. So let's not do that. We were very, very explicit on day one of the class about this. So we were hoping we won't have to have a conversation like this again, and we will not have it another time. Next time, you heard what the TAs said they will do. Any other questions?
And also, when we say like short answers, we just mean like don't overcomplicate things. So like that's what we mean when we say short. Like not like it has to be less than 50 words or we're going to stop reading it. It's like don't make it more complicated than it needs to be, because you're probably going to have more flaws if there's like more steps to it. So
like that's really just a technique for sort of distilling things in another part of the problem that should help to understand. Also, just keep in mind that we are here to help you. If you are having difficulty with a concept in the course, or if you are concerned about your grade, please come to us. We are here to help you. Yeah, that's all that I'm.
Any other questions?
Ask us more questions. Ask the TAs more questions while they're here. What else?
It's an Ask Me Anything session.
Yeah.
So during an exam, in general, actually, if you are not understanding definitions, I would look at the book, because there's actually a lot of stuff in SPSR that you guys maybe are overlooking. So the pumping lemma, there's a walkthrough in SPSR. Even one of his walkthroughs, like his examples, would have worked for question 1 on your homework. So I encourage you to look at it. So all of those definitions, most of the time they're going to be in SPSR. So, you know, if the next homework you guys are working on talks about incompressible strings. So he talks about what they are, he talks about why they exist and why we know they exist in the section. So I would encourage you first to go to the index of SPSR, look for your word alphabetically, and if it's there, go to that page. If you have other questions while you're working on your homework and you don't have time to office hours, I would encourage Wikipedia. It's a pretty good resource for it, actually.
Yeah, so the TAs have office hours every single day, including Sundays and Saturdays, and there's problem-solving sessions every single week. You know, I'm spending thousands of dollars of my own money on pizza for the entire semester. My gift to you, you know, all to encourage you to come in, to talk to the TAs, to solve problems, to collaborate in groups, and do it the right way. You know, there's no shortcuts to understanding this material. Just like there's no shortcuts to training for a marathon. You know, you can't wing it the weekend before, run like 100 miles the weekend before, and then you'll be trained for the marathon. No, that's absurd, you know. So you got to pace yourself, you got to work as you go, and many of you have done that, and, you know, we're not talking, you know, we're not trying to make you uncomfortable. If you've done all these things, you showed up in office hours a lot, you came to the problem-solving sessions, you are working in groups, you are not procrastinating on the homework and submitting them in the last few minutes before it's due, like some people are doing. That's a terrible sign that you're really not putting in hours and time and thought into the material. You know, and also if you procrastinate, there's more pressure on you to cut corners and look things up in the last minute, and then this is what's going to happen. So, you know, I try also, you know, we all try very, very hard to get you to not procrastinate, pace yourself, work every day. You got to be spending somewhere between 6 and 10 hours a week on this stuff, and closer to 10 and even more if necessary. You know, if you're just spending 1 or 2 hours a week, you're just kidding yourselves. And it's very obvious to us that you're doing that simply from what you're submitting. So, you know, there's still a good month plus left in the course. You know, it's not too late. But you got to start training, you know, for the marathon. You can't just show up, you know, when the event happens, whether it's a test or an assignment or a deadline or whatever it is. So ask us some more questions. Yeah. That's great. But if you don't understand the question, the TAs can answer them. Even on the exam, you can submit it to Piazza and they'll answer it within minutes.
We can explain what questions mean and basically give as much as we can say if you do a private Piazza post for exam questions. I would also just start writing down true things that you know about the material. So if you, true facts go a long way. If you start just writing down things that are like, as Professor Brunel will say, if you can use vocabulary terms in grammatically correct sentences, it doesn't mean you know what that means. So if there's a question on regular shuffle, for example, and you have no idea how it's supposed to work, if you say, well, I know the first two are regular languages, so they have some finite automata that accepts them, and then say, I'd imagine that if I wanted to prove its regularity, I need to construct a new one, that will get you half credit. Because you're talking about, you know what you need to do, you just don't know how to do it. So start writing down true things. Start what a regular language is, if it's about regular languages, what it has regular expressions, it has finite automata, and how you might be able to use them to solve the question.
Also, keep in mind that all the exam questions came from the problem sets, and they were posted since early in the semester for many weeks. So if you don't understand a question, the time to understand the question is not during the exam. It's 3 weeks before the exam. And again, that assumes you don't procrastinate. So procrastination is very, very damaging to you, whether you realize it or not. It's more damaging than you even think it is. I'm sure most of you realize procrastination is not good. It's much more horrible than that. So your question basically presumes procrastination in the very question that you're asking. If you don't understand the definition or the wording of a question, the time to have cleared it up with the TAs was 3 weeks, 2 weeks before the exam, or a week before the exam, or 3 days before the exam, not during the exam. Even though you can still do it during the exam. It's just too late.
Another thing is that partial credit goes a long way in this course. So we never actually give a 0 on any question, unless or until you have it completely blank. So if you write something, you might end up with something close to around 30% of the points. So write something that you understand from the question. Otherwise, rewrite the question, you might get some points as well.
Yeah. So for example, in the case of a shuffle, if you say, I don't understand exactly what it means, but I think it means this, and if it does, here's my answer, that's worth something. Even though you've had many chances to clear that up with the key. The shuffle came up over and over again in assignments. So.
One more thing is that if you still don't understand what the shuffle is, please come to office hours, we can explain it to you, because it's going to repeat itself through the problem sets and through exams as well. So homework 4 as well, yeah, true.
Yeah, ask us more questions, while they're here, yeah.
Around what's the timeline for when we'll get our midterm back?
We expect it within.
Our current plan, so the homework 3 grades are going to be released later today. Our current plan is next Wednesday-ish. Let's say plus or minus 2 days. So, yeah. Is that satisfying? You should have it. So homework 4, you have 2 extra credit problems, which are basically test corrections. You can go ahead and do those now if you know you got something wrong in the midterm. So basically, if you got something wrong, solve it again but correctly. Or if you got all of them right and you still want extra credit, solve it differently. So you will have them back before the homework 4 is due, but you're welcome to do those extra credit problems even if you don't know if it's right or wrong yet. And you can bring in your midterm to office hours and ask us like, hey, I know this is really wrong. How does it work? And we can help you with that as well.
What else? Yeah.
So yes and no. Yes, if you did not understand things on the midterm, you are not going to understand certain things on the final. But mostly it's going to be centered on things that you learn in the second half of the class. So Turing machines, recognizable languages, some of the NP problems, and some other oracle questions.
Yeah, but there will be probably references to finite automata and things like that and context free, not necessarily harping on them. But remember, a Turing machine is basically a finite automata with a tape. So if you say not cumulative, so you're going to talk about Turing machines but not finite automata, well, a Turing machine that doesn't use its tape is a finite automata. So in that sense, the material has no way but to be cumulative in some sense. Because if you don't understand A, B, and C, you won't understand D and E that build on the first 3. So the material itself is cumulative.
There will be questions potentially from every problem set.
Yes.
Yeah, potentially, yeah. Of course, the first problem
yes.
set, we mostly gave you most of the solutions by posting them online. So, we'll try to not replicate many problems on the final that were already given in homeworks. So that eliminates a lot of things, right? Or things that we solve explicitly in class are less likely to be on an exam because we gave you the answer. And, although we may just do that for the heck of it, just to see if you were listening. Or understanding or following along or writing things down or studying the notes. So look, we're trying really hard to help each and every one of you. We don't want to fail anybody. I have no quotas. If everybody does well, everybody gets an A in the course. I don't feel like I got to give only 20% A's and 20% B's and so on, like some professors might. But you got to help us make that happen. We really don't want to fail anybody, and we certainly don't want to drag anybody into honor but help us help you with that. We put a lot of resources and time and attention and effort at your disposal collectively, not to mention a lot of free pizza. So I'm not sure what else we can do. We're doing everything we can think of to help you out. But you got to do some of the heavy lifting and meet us halfway and not cut corners by cheating and plagiarizing and just looking things up and writing things down that you don't understand. It's very obvious when you write something that you don't understand down, that's obvious to us that you don't understand it. There's 20 different ways we can tell. Maybe because you don't understand what you're writing, you also don't understand how easy it is for us to see that you don't understand what you're writing. But it's very easy, trust us on this. We've been doing this for a long, long time. We know all the websites that you're searching. Yeah.
A question about referencing things that happen in class. If, for instance, there's an example in class like 0BN, 1BN, 2BN, and we go through and prove that it is or is not context-free, on a homework or exam or whatever, can we say, this is just like this example in class and just leave it at that, or should we go into more detail?
If you want to use as a lemma in proving something else, a 0 to the n, 1 to the n is not regular, or 0 to the n, 1 to the n, 2 to the n is not context-free, that's fine. Just state that, say we mentioned in class, maybe even say, it's true by, the pumping theorem, just so we know that we know what theorem causes it to be true. And that's about it, all you got to say. So we're not talking about stuff like that. We're talking about real egregious cases of, copying entire paragraphs that are verbatim or almost verbatim from the web, or even worse, copied from the web with some of the variable names changed. That wouldn't fool a compiler, and that wouldn't fool us. It's just kind of silly. Don't waste your time like that. Put that time in understanding what's going on, going to the TAs. They're there every single day, literally, every single day of the week. Yeah.
If I submit an answer that I think I understand, but when you guys grade it, it's like obviously wrong, what's the difference between getting a problem wrong and not understanding the answer?
The main difference in this context is whether when we Google your answer, we find it online. That's pretty much the litmus test, which means it's not just something that you came up with that is wrong. It's something that you copied, and you don't even know whether it's right or wrong or what it means. And it's very clear which is which in absolutely almost all cases. It's pretty dramatic from our perspective.
I just wanted to add one thing to the previous answer. So anything in green over here is an example of a particular language bringing in that set. And you can use that directly and say that from the extended Chomsky hierarchy on the slides, it's there, and I don't need to prove it. You don't need to prove it. Nobody needs to prove it.
Yeah. What else?
That was one of my questions. So, for example, A star is a known regular language. Finite languages are all regular. Those are all things that we can use without.
Mm-hmm.
The second thing, the extra credits on homework 4, how does that weight relate to the weight of the problems on the exam?
So the extra credit's not going to go on your exam, it's going to go on your homework. So your homework, I believe, is worth 180 points, and the extra credit, each of them are worth 20 points. It says it on the first page, basically. So you can do the math. So the maximum score on that is a 220 out of 180.
Which will be extra credit
type
on
it
the
into your
homework.
calculator. So it'll go directly on homework 4, not on your exam.
Do we want to extend the same strategy we did last semester? If anybody did cheat on the midterm, do we want to give them the option of coming forward before we finish the grading? Is that something we want to?
I'd be all right with that.
We might discuss that offline, where you can't hear everything we're saying, and go about it. But if you did cheat on the midterm, we have not looked at them yet, or not thoroughly. So start thinking about if you want. I would encourage you to come forward regardless of our decision.
Yeah, so we'll talk about it. But last semester, we offered people the opportunity to come forward, admit that they cheated in the midterm, and then we were more lenient. There would still be a penalty, right? And the penalty wouldn't just be 0 for the answer. Some people even start arguing with the TAs about, okay, so yes, I copied the answer for numbers 3, so just give me a 0 on that, and everything else should be fine. No, not exactly. Right? When you try to rob a bank and you run away with the money and you get caught, the penalty is not just, just return the money to the bank and we're good. Exactly, it's ridiculous. So please don't do that to the TA. Whatever penalty they impose on you, don't come back, it's too much. They can take you to honor, get you expelled from the university. That's how high the penalty can be. So if you get a 0 on the assignment, you're actually very lucky that that's all they decided to penalize you with. Okay, so keep that in mind. Keep it in perspective. This is serious stuff. I mean, people lose their education, their careers over stuff like this, and it's becoming worse and worse over the years as there's more websites and companies that basically their business model is we'll help you cheat if you pay us, like Chug and other.
Just FYI, we have access to a check account.
We have a theory Chegg account, so if you think that we can't see those answers, you're wrong.
So if you post to Chegg, you actually be posting to their account. You know, so that'll be even more ridiculous.
We may answer your question and be like, interesting question. This reminds me of a midterm question.
So please don't do that stuff. You know, it's very easy to catch. Just so you know. You know, I mean, it's.
And Chegg will de-anonymize you if we ask them to.
Yeah, we had, you know, we had issues in the past with Chegg. We contacted Chegg, and Chegg told us who you were, even though they promised anonymity. When the university bears down on them with all of our legal infrastructure and so on, Chegg cooperates. They fold like a Robert Mueller witness. Just so you know that too.
Another interesting thing was some people actually try to put pictures in of text. It's hard for search algorithms to work on it, but it's not hard for us to do that. And it's obvious in certain cases. So even if you want to post something and you're trying to post it as images, algorithms have gone up higher and it's become more powerful, and it does the recognition on top of that, so it won't work that way as well. Before it did, now it won't.
Any other questions? All righty then. Now we can talk about complexity theory. Our wonderful TAs. All right, so the Chomsky hierarchy. That's a segue, huh? So we talked about context-free languages, context-sensitive, decidable languages, and we define these complexity classes up here: polynomial space, exponential time, exponential space. Because now we're talking about what's doable within certain times and space consumption of resource-bounded computations. And there's many unanswered questions, you know, whether P is equal to NP, and there's many others, dozens, even hundreds of other open questions are even more difficult than P is equal to NP, because P is equal to NP will be a simple consequence corollary of some of these more difficult questions. So last time we talked about the time complexity hierarchy. We said that no time complexity bound is enough to recognize all decidable languages. There are languages that require more and more time or space resources to compute them. And they're all decidable. There's nothing undecidable about them. They just require more and more time and space. So we showed that there's no time function that within which you can compute all decidable languages. In other words, another way of saying it is that for any time-bound t, there's a decidable language that requires more than t time. It's not in d time t of n. And the proof was by diagonalization, right? You construct a function that's decidable, but not computable within that time bound, no matter what the time bound is. And the same holds true for space. So for space, there exists always languages that are not decidable within any given space bound. Okay. Again, same proof as before using diagonalization. And also dovetailing comes in quite handy here when you enumerate all the Turing machines and inputs to Turing machines and so on. And we left off with Savitch's theorem. We mentioned it, but now we're going to prove it. This is a deep theorem. So we'll take a deep breath and let's go for it. So basically the theorem says that to get non-determinism gotten rid of, to eliminate non-determinism in a space-bounded computation and make it deterministic computation instead, suffices to at most square the space. You pay a penalty for eliminating non-determinism, but the penalty is only quadratic. It's not exponential or any other thing. So the idea is to simulate the non-deterministic computation, space-bound computation, within deterministic space-bound of at most quadratic amount of the original, respect to the original amount. And we're going to basically reuse space very, very aggressively at the expense of time. And you'll see in a minute how that works. So we're going to trade off a lot of time for staying within a very small amount of space. It's like having a little tray table in your airplane seat in front of you. It's only 1 square foot, and you're going to keep shuffling around your laptop, your PC, your phone, your meal, your drink, your book, your sweater, and a tiny amount of space. But with all this shuffling in time, you can use a 1 square foot table. It's just very inefficient in time, but it's efficient in space. It's only 1 square foot. That's exactly what we're going to do here on steroids. This is going to be very dramatic reuse of space at a very expensive use of time. But we are trying to conserve space, not time. So it's okay to waste time if what you're trying to conserve is space. Okay. All right, so here we go. The idea is by simulation. I'm going to reuse space and sacrifice a lot of time. So consider the Turing machine computation is non-deterministic, so some computation in non-deterministic space f of n. That means you start at the start state here in purple, and you're going to end up in some final state here in double red circle. And in between, you're going to switch a lot of different states. And by the way, a state here is not just defined as automata state, like the state set of the automata or the Turing machine. It's the entire contents of the tape. So each state here is basically a snapshot of the Turing machine at that moment, including all the contents of the tape and where the read-write head is, and of course, which state the machine is in at that moment. So that's kind of a snapshot. When we say state, we mean the generalized state, the snapshot of that machine at that moment. Question?
To do this, wouldn't you just need to do a depth-first search instead of a breadth-first search of the deterministic on the non-deterministic?
So he's saying, can't you do a breadth-first search and keep track of all the different states?
A depth-first search instead of breadth-first search, so you don't use a lot of memory.
Oh, a depth-first search. Well, but even if you, so in a sense, we are doing that here. But you have to be careful because some paths go on forever. So if you start searching them forever, you might get into infinite loops. And also, if you're going to go down a tree and do a depth-first search, you're not just paying for the node that you're looking at now, how much space that node takes. Because if you don't keep track of other things, you won't know where to come back and recursively search the rest of the tree. You have to pay something else. You have to pay for the recursion, you know, or the search of the tree. You have to kind of mark where you've been so you know not to go there before. So in order not to go there before, you have to keep track of all the states, or at least many of the states, intermediate states, before you're getting to the one that you're simulating now and the one below that and so on. Because if you don't keep track of anything there, let's say it doesn't pan out, where are you going to go? Back to the root and start over? But how do you know that you already did this branch unless you marked something about this branch? And that's going to take space. And there's a lot of branches. So you're going to have to spend a lot of extra space just remembering where in the search you are. And when you do a depth-first search, usually you do it recursively, and the recursion keeps a stack around. And that stack has stack frames. And in this case, each stack frame will be the entire state of a machine at that moment, a snapshot of the state. And a snapshot of the state has f of n space in it, because it's a complete description of that Turing machine at the moment with its entire tape and its entire contents of that tape. So the stack frames themselves have f of n space. So, but we will do something like that, but you have to be a little careful. But it's a good idea, and this theorem sort of nails that idea down and does it in a way that doesn't more than square the space. You'll see in a minute how it goes. Also remember that the space you're using is f of n, but this path from start state here in purple all the way to a accepting state there in double red, the length of this path is how long as a function of f of n. The space you're using while you're doing this is f of n. But how many state changes can you have within f of n space? Take a wild order of magnitude kind of guess, or asymptotic kind of guess. Let me give you three options. The length of this path, where you're using at most f of n space along this path, the length of this path is f of n. That's choice one. Choice two, some polynomial of f of n, like f of n quantity cubed, or to the 5th power, or something like that, some fixed polynomial of f, or exponential in f of n, like 2 to the f of n, or some constant c to the f of n. What do you say, A, B, or C? F of n, some higher polynomial in f, or exponential in f? It's exponential in f. Why? if you want to use n bits, and that n bits can be anything you want to set it to, and you're churning and computing over this n bits, that's all you got is n bits of storage. How many different states can this n bits be in the worst case? N squared, n log n, 2 to the n. So it is exponential in the amount of storage you have, but the amount of storage you have is f of n. So it's exponential in f of n. So it's a very long path. So another problem with going down this path, depth first, it's very, very long. So the tree is not bounded by this, and it's bounded by this. And you have to somehow figure out how to do depth first search on a tree that's huge. The depth of the tree is this. It's not just f of n. Any questions so far? Because here comes the hard part. This was just preliminary. So we need to simulate this branch and all the other branches. So we are sort of doing depth first in the tree. But the tree is huge. Look, if the tree is that deep, imagine how wide it is. How wide is this tree? Take a wild guess on that. Let me ask a slightly simpler question. If you have some sort of a binary tree, and the tree is k deep, how wide is the tree? Roughly 2 to the k, worst case. Right? But this tree is not f of n deep, it's c to the f of n deep. Deep. How wide is this tree? 2 to the c to the f of n. It's not even 2 to, it's d to the c to the, it's double exponential. And you need to search this entire darn thing, depth first if you'd like. Because certainly searching it breadth first is hopeless, right? Because it's not just exponential wide, it's double exponential wide. It's exponential high. So forget breadth first search. We have to store entire levels at a time. Obviously, that's completely hopeless. It's 2 exponentials away from hopeless, not just 1 exponential away from infeasible. It's really bad. Okay, so it's not obvious how to do this. So how do you search this whole tree for a final state, beginning with an initial state, efficiently? And by efficiently, we mean space efficiently, not time efficiently, because we are conserving space here. And we can waste time. That's okay now, to waste time, because we're trying to conserve space, not time. So it's a divide and conquer approach combined with depth first search. So here's how it's going to work. I rewrote the path here so this long path here, this particular path that we're searching for, not all these other paths, is right here. So here's what we're going to do. We're going to pick a midpoint along this path. And we're not sure what the midpoint of this path is, so we're going to guess, and by guess I mean we'll try all possible midpoints. So we'll brute force try all possible midpoints of this path, and let's say the midpoint is here. And remember, we're not just picking one. We're picking all of them and iterating over all of them. And what's going to happen next is going to be happening for all possible potential midpoints that we're going to iterate over. In other words, we're going to exhaustively enumerate all possible mid-states of this long computation. And for each one of those, we're going to check that it's a valid intermediate state. How do we do that? To make sure that this state is reachable from the start state, and separately verify that from this intermediate state you can reach the final state. And if both of these are true, there's a way to reach from the initial state the final state, and you found such a path. So we break it into 2 pieces, check each piece separately, independently of the other piece. How many understand this strategy so far? And what intermediate node do we do this for? All of them. Very inefficient in time, but efficient in space. And this is about space conservation, not time conservation. So, and by the way, when you check this path here, you can reuse the space after you have checked this path. So you check this path here first, if such a path exists, you check that first. And once you do that, you can clear the slate, initialize all that space that you use to check that first path, and then use that space to check the second path. So we're using that space twice here. Okay. And for each one of those choices of the intermediate node, of which is an exponential number of them, because each state here is f of n bits or tape squares or whatever, it's f of n large in space. Each one of those, you're going to reuse the first and second checks the space again and again and again. So there's already heavy reuse of space going on here. Not just twice, but twice for every single choice of the midpoint. And there's an exponential number of choices for the midpoint, because the midpoint is f of n space in all possible combinations of bits within that space. We're not done yet. All we did is the first level of the recursion. And how do you check that there's a path from here to here? That's the same problem of checking a path from here to here, just smaller version. So to check there's a path from here to here in green, find an intermediate point somewhere along this path, and for that point, check to see if there's a way to get from the start state to this midpoint, and from that midpoint to this green midpoint, and separately do the same computation there for an intermediate point there. So to check that the green is a midpoint, you need to check that these two reds are midpoints. How many see the strategy? Okay. And to check that the red is a midpoint, guess what we're going to do next? Same thing, repeatedly. All right? Find an intermediate point here, see there's a path from here to here, and then from here to here, and then you know that the red is good, then clear the slate, check this red separately, then clear the slate, and you know that the green now is good because you have the two reds, then clean the slate, and then do the whole thing for the right-hand side recursively all the way down. There's an enormous amount of time wasted here. Because this red path could be exactly the same as this red path, and the same as this red path, and this green could be the same as that green, and this red state could be the same as that green state, and so on, because we're checking all of them at every point in this recursion. So when we check the red point, we mean all possible candidates for the red point, all exponential number. And for each one of those, you got to do the sub-check. So you check all exponential number of midpoints between, and so on and so on. It's hard to even describe how wasteful this is in time. But it all reuses the same space over and over and over and over and over again, because all these checks are independent of each other. And when you get to the bottom of the recursion, you'll know. Right? And as it unfolds back up, you computed whether there exists a path, the original path from this initial purple start state to this final double circled red state. And then you have found such a path, which means you discovered a path in the non-deterministic computation that gets you from an initial state to a final state, which means the computation accepts. And the next question is, how much space did you waste doing all of this? Because the time was horribly inefficient. But the space is not so bad, it turns out, because you can reuse the space over and over and over again. Each pair of computations, you reuse the space here, and then wipe it clean, and then the same space, reuse it for the second computation, independently of the first. Okay, so how much space, is there a question so far? Yeah.
Well, how do you know that that final state is the one that the non-deterministic can reach? Because there's going to be many final accepting states.
Yes, excellent question. He's saying, how do you know that this is the final state that we're going for? Because there's other final states that we could have gone for instead that could be different than that one. Excellent question. Beautiful question. What do you say to that? Try them all. Remember, we're not concerned about saving time here, just saving space. How much space does it take to try them all? If I want to try all strings of n bits, n could be 1,000, 1,000,000, 1,000,000,000, it'll take how much time? How much time to go to cycle through all strings of n bits? 2 to the n. How much space to cycle through all strings of n bits? But we'll get to that, yeah.
But if you do what you said by aggressively switching out, you only have to worry about your longest one. That's the max space you need to fit it.
Yeah, so how much space to cycle through all strings of n bits? N space. 2 to the n time, but only n space. And how do you keep track of which string you've seen before or not when you cycle through everything into all bit strings of n bits? How much extra space does it take besides storing the actual string of n bits? Not a trick question. What does the piece of code look like? For I goes from 1 to 2 to the n, you know. Keep generating strings, you know, one at a time. So you need to store a counter, I, that cycles through. Right? If you want to count from 1 to the 1, if you want to count from 1 all the way up to 2 to the n, how big is your counter? How many bits do you need to represent quantities as large as 2 to the n? Again, not a trick question, it's an easy question. Yeah. N. The log of whatever the quantity is, and quantity is 2 to the n, so the log of 2 to the n is n. But we're already using n space to store the strings, so we're using an extra n space to store the counter, counting the strings, is no more than n anyway, and n plus n is equal to n, asymptotically speaking. It's really equal to 2n, but when you go to big O notation, it ignores constants, so 2n is the same as n, they're both linear. Okay. So keeping track of where you've been is not that bad, and in particular, keeping track of where you've been here, the length of this whole path is up to c to the f of n. But how many stack frames do you have to store in the recursion stack as you keep dividing and conquering and going deeper and deeper into the recursion? If you're recursing over a path of length k, and you're doing this in divide and conquer way, let me ask you a different question. Merge sort. How many heard of merge sort? You know how it works? Okay. How deep is the recursion stack in merge sort in the worst case if you're sorting n objects? How many recursion levels are you going to have? Say it loud, say it proud. Log n. Logarithmic in the input size. So here too, it's logarithmic because you're going half, and then half and a half, and then half and a half. By the time you recurse up and do this thing, the stack is cleared, and now you're recursing on this left side using the same space, so the recursion starts from scratch. So the recursion depth is logarithmic in the number of objects you're recursing on, if you sort of divide and conquer into 2 equal pieces like merge sort. So this is the same thing true here. So the length of this path is c to the f of n. How deep is the recursion? Another easy question, not a trick question. F of n. You know, maybe modulo a constant if c is not 2, but yeah. So the recursion depth is f of n. Each recursion stack frame is how wide. Each state that you're storing as you're recursing, and you got to keep track of all the states so you know where to continue from to the next state and so on. How wide are these stack frames of the recursion stack? How much space does each frame of the recursion stack require? What's that? It's the length of the entire space, a snapshot of it's a state. So the state is the entire snapshot of the machine. The machine has at most f of n space. So how much space you need to store a state of the entire machine? F of n. So each stack frame as the recursion stack unfolds, each level of the stack is f of n space, kind of instant snapshot of the machine. And there's f of n levels in the recursion, like you said. So the total amount of space you're using to implement this recursion is what? Recursion is f of n deep, and it's f of n wide. F squared of n, there's your theorem. End of story. We just proved it. So, and this is a deterministic computation. So what have we done here? We took a non-deterministic space-bounded computation and can bifurcate all over the place. We did a depth-first search of it, sure enough. But we were careful not to use too much space, because the depth is horrendously long. The depth could be exponential in f of n. And that's Savitch's theorem. So to get rid of non-determinism in space-bounded computations, at most you have to square the space, not exponentiate it. It could be much worse. For time, the best we can do is exponentiate as far as we know. But that's a p is equal to np question.
How do you keep track of the branches you check?
Yeah. So how do you keep track of all the branches? So you start going down some branch. Let's say it's, let's say you start from this end. So you go down this branch here, and you reach some final state, or some dead end, and then you go back up, and then try something else. Then you go back up and try something else, and go back up and try. So you're doing a depth-first search. How do you know what the next state is? The state, remember, is just an instantaneous description of the machine. It's some snapshot of the Turing machine. So if you have a tape that contains a certain amount of information, bits on it, to get to the next state to try, take them in order. Just add one bit to it. Add one. Consider that to be a big binary number. All that f of n space, consider that just one big integer. Add one to it. And you get the next one. And then you try that. Add one to that, then you try that. Now, as you, and that's basically what you do. Now, you know if two states are neighboring states simply by looking at both of them and see the transition function given the first state will get you into the next state with one transition. So you know if two states are neighbors with respect to the transition function. Right? So that one is easy to do. So the whole thing is a very clever, very space-thrifty simulation, but very time-wasteful simulation at the same time. But we're trying to conserve space, not time, so we're good. Yeah.
Just for clarification, that f squared of n is only referring to the stack and maintaining the stack, so there's also a separate f of n that's for the workspace itself, right?
Sure. Yeah, he's right. He's making an interesting point. He's saying f of n squared is the stack space. But you also need to keep track of a few other things that are of themselves size f of n, like the copy of the tape, for comparison to something else, or maybe a few counters, or whatever else you need. But what's f squared plus f? Asymptotically speaking, it's f squared. So you can use as many other f's as you like. It's like any constant number, as long as not some hugely growing number. In fact, you can use f of them, and you're still okay. So you can use extra space. They get swallowed up asymptotically in the f squared because that's the dominant term. So you get the rest you get for free, basically, asymptotically speaking. Just like in merge sort, the whole thing takes n log n time. So if you need an extra n time to do other things, like clear the array before you start or whatever it is you want to, you get that for free. Because that's not the dominant term in the asymptotic growth. Okay, other questions? But it's good to think about these things. Make sure that it's free and not costing you and changing the result. Okay, so we just proved Savitch's theorem. That's, there's Walter Savitch. That was a brilliant insight. And again, let's look at what the theorem says. The theorem says, to get rid of non-determinism in space, suffices to square the space. And now you got it deterministically. This is the space analog of the P is equal to NP conjecture. The P is equal to NP is exactly this, but instead of for space, it's for time. P is equal to NP says, if you want to get rid of non-determinism in time, suffice it to exponentiate the time. But we don't know how to do it in less than exponential in time right now. So if you do something in non-deterministic polynomial time, you want to do it deterministically, you can do depth first search or breadth first search even, and expand out the whole tree, track the whole tree, and then you'll know what happens. But that'll take you exponential time. We don't know how to do it more succinctly with any kind of shortcuts than exponential brute force search. The P is equal to NP question is whether you can take a shortcut to exponential. This one, for space, says yes, you can. The shortcut is not using the whole exponential amount of deterministic space, but quadratic space suffices. So this is the space analog of the P is equal to NP kind of time version of the problem. Why is NP equal to P so much harder than this? I mean, this wasn't trivial either. It took us a whole 2 slides, a lot of explanation. You know. Why is P is equal to NP so much harder? Because time is not reusable. Space is reusable. It's not clear how you could reuse time. In fact, intuitively, you can't reuse time. So shortcuts are much harder to come by when you want to conserve time. Conserving space is just wipe it clean and then reuse it. That's easier to do, more straightforward, not as complicated to see that it's possible, and so on and so on. Algorithmically, it's more tame than trying to be efficient in time. Yeah.
So I guess by analogy, like, is it okay for us to assume that, like, you can represent pretty much any tree as a two-dimensional array, and that's the analogy here is that you basically have a bifurcated tree and we're representing it as a two-dimensional array?
Well, when you say two-dimensional array, you're referring to the stack going on? Well, so if you want to represent the entire tree, you need a lot more than just these waypoints. These waypoints are a very, very compact representation of that tree where you're recomputing the tree from scratch every time you need new portions of it. So this point here could be the exact same point as this one, the exact same state as here, because you're trying all of them. So this red dot could be exactly the same state as that red dot. How many can see that? It could also be different. But let's say this red dot is the same as that red dot. You're going to do this left side of computation, find the right red dots here, make sure everything works, erase the slate, and then come back here, and now you got to find this red dot. You will never know that you've already seen it before. You cleared the slate. So now you're going to have to recompute that one from scratch, and you may have to recompute it again and again and again at other levels of the recursion too. It's a huge waste. I'll give you an example of how big of a waste this is. Like if you take some real life analogy, let's say you want to save space in your wardrobe. You only have one tiny little drawer. That's your entire space for your wardrobe, and you want to save your entire wardrobe there. And you know, every time you need a shirt, a pair of pants, you know, it's got to be in that space. So there's a way to do it in a very space conservative way. It'll waste a lot of time. And the way to do it, you know, you can keep a few rolls of thread and yarn in that drawer. How many see where this is going? You want a shirt? Go into the drawer, take the thread and the yarn, start knitting a shirt. You need a pair of socks? You know, take another roll, knit a pair of socks. You know, now you're good. You can go have your day, come back, unknit the shirt and the socks, roll it up back into the yarn balls, thread balls, put it back into that little space. Next day, repeat. You see how inefficient that is? In time. But how beautifully efficient in space it is. Only it's one little tiny shoebox with a few balls of yarn and a few rolls of thread, a couple of needles. That's your wardrobe and you're good. Now, in real life, this will be ridiculous, kind of a strategy. But it will work. How many see this could work? Of course it could work. It's just very, very, this is what this is doing. Every time it needs a new shirt or a new pair of socks, it has to, from scratch, compute exactly that thing from scratch, even though it has seen it before. Because tomorrow, when you need the same shirt again, you're going to have to re-knit it from scratch again. And again, and again, and again. And occasionally, you may want to wash your yarn. You know, I don't know how you put it in the sink or something. It's not too dirty, you know. But this is what's going on here. It's extremely inefficient in time. But it's very, very efficient in space. It's probably the most dramatic, extreme example of space-time trade-off that I've ever seen. Actually, and I've seen plenty. Okay, so that's Savitch system. Any other questions or comments about this? All right. So a corollary to this is very interesting, that non-deterministic polynomial space is equal to deterministic polynomial space. That's a corollary to Savitch's theorem. Why? Because non-deterministic polynomial space is the union over non-deterministic polynomial space of all possible polynomials, n to the k for all k. Right? That's a definition right there from a few slides ago. But now, from Savitch's theorem, non-deterministic n to the k is contained in deterministic n to the 2k. Right? How many see that? It's a square. N to the 2k is a square of n to the k. And now we've gotten rid of the non-determinism. But the union over all deterministic space classes of n to the 2k is the same as the infinite union of all deterministic space classes of just n to the k, because you're going for all k. So you don't care if you're jumping by 2s or by 1s or by 5s or by 10s. You know, all polynomials will be there of all possible, you know, exponents, and you got all polynomial space in there, and that's just polynomial, deterministic polynomial space, which is equal to deterministic to non-deterministic polynomial space. So we got this theorem here, which is really a corollary to Savitch's theorem, that non-deterministic polynomial space is equal to deterministic polynomial space. For time, the analog of this is p is equal to np. We don't know. But for space, we sure know that p space is equal to np space. For time, we don't know that np time is equal to p time. P is equal to np. That's worth $1 million still. So this solves the p is equal to np question for space. And now you know. Any questions about that? So another way of saying it is the polynomial space is invariant with respect to non-determinism. Non-determinism doesn't change your polynomial space. Deterministic or non-deterministic, it's the same class, the same set of problems or languages that you can recognize in polynomial space, deterministically or non-deterministically. And we already mentioned that for polynomial time, that's still open. Okay? So a few other theorems. Deterministic space is closed under complementation. That's easy if you have a language, if you want to recognize the complement of the language, if that language was polynomial space computable, to recognize the complement of it, just do the original computation, just negate, flip the bit from yes to no, no to yes. Now you're computing the complement of the language within the same amount of space, because flipping a bit doesn't take any space. Question?
If we solve p equals np for time, can we use that solution for space as an alternate solution to the space problem?
Good question. If you solve p is equal to np for time, will that be an alternate solution for the space version? Well, it's hard to imagine that it'll be any simpler than Savitch's theorem, for one thing. And space and time reuse or use in general has a different flavor to it.
You choose not to reuse space, though, and then that can be like, the solution will require that you don't reuse space because you can't reuse time. But you could always say, hey, I'm not going to reuse any of the space. And
yeah. Yeah, you may get a weaker version of Savitch's theorem. You know, so for example, if you want to show that p is equal to np and you somehow convert that to space kind of analog, you may get that that n space of f is inside a d space of f cubed, or f to the 4th, or f to the 10th, or something like that. And you may be able to pull it off. It will not necessarily be better than Savitch, or even equal to the square only of Savitch's theorem, depending on what technique he used there. That's a very good question. It's very insightful. Okay, so to complement deterministic space, you can simulate and then negate. That's easy. Here's the hard part. To complement non-deterministic space, you can't just simulate and negate, because you have to search entire giant trees, and that could take a while, and there might be recursion involved. But it turns out you could do it some other way. It's much more complicated. It's basically an analog of Savitch's theorem, but it turns out that non-deterministic space S is equal to co-non-deterministic space S. In other words, you can recognize all the complements of the languages in deterministic, non-deterministic space S within the same space bound, S. So basically, non-deterministic space is closed under complementation. It was a major result in '87. I remember when Neil Immerman first came up with this. It was, big headline news, actually. It was not quite the p is equal to np kind of revelation, but it was up there, because the question has been open for decades. And it uses techniques similar to Savitch's theorem, heavy space reuse, and using recursion and divide and conquer, and so on. Now, for time complexity classes, we don't have any kind of similar results to Savitch's theorem, not just for p is equal to np, but to any of the other analogs, whether exponential, non-deterministic exponential time is equal to deterministic exponential time, or any of the other analogs. We don't have any time analogs of Savitch's theorem. It's again, because Savitch's theorem does such heavy reuse of space, it's peculiar and particular to space reuse. time, not only we can't reuse it so heavily, we can't even reuse it at all in some sense. Although when you design more and more efficient algorithms, you can think about taking some solution and folding it in time to make it more efficient, like sorting. Like going from bubble sort that's n squared to merge sort that's n log n. You can think about it as some abstract way of taking a long computation and folding it into a shorter computation that still does the same job, but that transformation is very complicated. It's basically algorithmic redesign of the algorithm. You know, it's not some straightforward simulation. It's more efficient, strictly speaking. Okay. So with respect to NP and co-NP, that's still open, right? And on the class website, there's a book by Dexter Cozen, Theory of Computation, and that theorem is actually proved there, the Immerman theorem, showing that non-deterministic space is closed under complementation. And the proof is not that long. It's only like a couple of pages. And for extra credit, I urge you to look at that. And there's a book by Immerman where on the cover, it shows you the extended Chomsky hierarchy on steroids. And here are all the classes. I'm going to reproduce this book cover here. And you can see the regular languages down here. And there's NP up here and co-NP. There's PSPACE, exponential time. All the decidable languages are here. The recognizable languages are there. And there's all of sigma star up here. The whole thing is all of sigma star. There's the deterministic logarithmic space, non-deterministic logarithmic space, and so on. So this is kind of a different view of the Chomsky hierarchy, with a few other sets here that we didn't mention. Of course, I prefer my own version. That's why I put so much effort into this slide. And this shows you kind of more clearly where the main waypoints are and, you know, tourist attractions on this beautiful chart, the regular languages, the context-free languages. And now we proved a couple extra things. So I'm showing you this context, this diagram in this new context of what we just proved. So we proved, for example, that polynomial space deterministically is the same as polynomial space non-deterministically, and both are equal to co-non-deterministic polynomial space. The complements of all these languages are also in there by Immerman's theorem and by Savitch's theorem. So these two equalities are due to Immerman and Savitch that we just proved or discussed these theorems. And of course, exponential space is equal to co-exponential space. That's also a consequence of Immerman's theorem, that any space class is closed under complementation. Any space class is closed under complementation. So now we have a few more things to add here to this diagram, and we'll have more to add besides as we go along. So again, you need to read the book on all this and study it. This is abstract stuff. Now we're in deep theoretical waters at this point. It's no longer the shallows. So you got to really stay on top of your game. Talk to the TAs, read about it, and we'll see you around.
Of the whole assignments, and does it usually have this much space at the top of each?
Can you do me a favor? Press the off button on that video and bring the whole tripod down here. Thank you. Yeah.